Alright, let's do some of steel design concept in ETABS. I'll be comparing one manual analysis and compare the same with the design which I've received from ETABS. First, let's understand some sort of combinations right here. Clearly, I was from IS 800 2007. Read all these assets here. From IS 3.5, 1.5, 3.3, table 4. We got some of the combinations here. It's dead load, live load, wind, and earthquake load is given here. So there's nothing more to explain. These and all are the combinations. You can either apply combinations manually or you can go for automatic combination. While getting into automatic combination, these and all are the combinations which will be provided by ETABS while we are picking up the auto combinations here. Alright, next thing we'll have to find out epsilon. This one is Fy. It's totally depend on Fy. This is root of 250 by the grade of steel. We got 250, Fe 250 grade steel and Fe 345 grade of steel here. Alright, in table 3.3, I got some of the limiting weight thickness ratio. Whether we will be picking up the section is plastic, section is compact, or section is semi-compact based on these numbers here. Let's get into the numbers later on. We got flexure compression for rolled eye shape, which will be all this eye section will be made by one single section hook. FB build-up sections here, build-up section, the flange and the web will be separated and will be maybe welded or bolted. We got axial compression. The force will be just only the axial compression, and that's it. Alright, that's it. Cool. Alright, the problem is right there. You got a force 1 kilonewton acting right axially. You got moles of elasticity, Poisson ratio, and shear modulus right here. Alright, and also we got some of the properties of steel, Fy and ultimate strength, and I got the section is ISMB 350. Alright, before getting into ETABS, let's understand a bit more theory. The first thing is the partial factor of safety for buckling and yielding. The factor of safety as gamma MO is 1.1. Alright, for RCC, this number is 1.5 and 1.15. For steel, the factor of safety is 1.1 as... Okay, we will be having the partial factor of safety 1.1. Alright, got the partial factor of safety. Now let's get into the calculation part. Alright. Got moles of elasticity, we got Fy, the section is ISMB 350. All these parameters regarding to ISMB 350 will be right there in steel table, or you can download the asset from the internet. You got the member length in Y direction. As you can see, if we're taking the top view of the I section, you got local Y axis will be right away in the horizontal direction. Local Z axis will be right in the Y direction. Basically, if you're taking Y direction will be horizontal, this will be vertical, and the local 1 axis will be right away through the length of the beam. So this is some sort of orientation which we are not familiar in ETABS or any software. So the total unbraced length, okay, which is K into LZ, you know, the K is always taken as 1 if we have any sort of fixed support here and the load is acting axially, the K will be taken as 1. So the length of the beam is 3 meter. As you can see from the problem, length is given as 3 meter. So gamma MO is 1.1, as you can see, that's from table 5.4.1, and the load is 1 kilonewton. So with all these things, let's get into the section compactness. First, we'll be finding out epsilon is 1, so epsilon is root of Fe. 250 by Fy, as the grade of steel is 250, the number is taken as 1. Let's find out whether the section is plastic or elastic. So for that, understand the load is getting in the axial direction. We can take out, let's read the problem. The section is, maybe the single section is right here, so we can have this sort of section, flexural compression. So the compression is measured in the flexure. So we have flexural compression right here, and the shape is build-up I section. And for build-up I section, we will be calculating B by TF and 8.4 epsilon, as epsilon is 1. So mu p is got 8.4, and be finding out B by TF right here. So B by TF, it can be like getting here, B is 140, thickness of flange is 14.2 here, dividing, we'll be having a 4.93 right here. So we know the number plastic in mu p is more than mu a, so you got 8.4 is much bigger, so the flange is plastic, as mu p is greater, the flange is plastic. Alright, let's find out the non-dimensional slenderness ratio right here. So that will be always h by bf, something we can measure right from here, h by b for this I said is 2.5, which is greater than 1.2, so we can pick up this option right here. So anywhere among this will be in our answer. And also we have thickness of flange is less than 40 millimeters, so TF is less than 40, so the buckling class will be A and B. So we got it, buckling class will be A and B. From table 7, this one is the table 7. I got to find out A and B, be finding out the imperfection factor 0.21 and 0.34. With that said, I'll be finding out what's happening in local Z direction. That will be finding out the Euler's buckling stress pi square into moles of elasticity. That number divided by the length, unbraced length in that particular direction, Z direction, by RZ will be right away from the steel table. Got this number here, and you got Fy by this number will give you some answer for gamma, for lambda Z. And 0.5, you'll be finding out value for phi, which will be substituted in the stress reduction factor, which will be multiplied by a number of Fy and factor of safety. So a lot of calculations is going on in manual case. So you got 0.5, 1, alpha, which is the buckling class A, gamma minus gamma is, you just got right away from here. Okay, so the phi is 0.532, and that phi will be placed right into this formula to get up the stress reduction factor. And finally, the stress reduction factor will be multiplied by y and factor of safety to get the FC. This will be the axial force on the asset. Same thing, we got B. Right now we have completed the calculation by using A. Now you got B, which will be considering the buckling class in the local y direction. So digging up, same thing, alpha, you got to find out the buckling stress, you got to find out gamma y, phi, stress reduction factor, and finally you got to find out FCD. So you got two numbers in local y, you got 110, and in the local z you got 255. Pick up the minimum number, so which is 110. That 110 shall be multiplied with the cross-section area to get the corresponding force right in here. So alright, for now manual calculation is over. Let's find out what's the same thing happening in ETABS. Alright, in ETABS, creating a new model. Alright, grid spacing is not important in here as the story height is 3 meter. We are not drawing anything in the x and y direction. Everything will be considered right in the z direction. The sole thing that we require is first is we can have a steel grade FA 250. So in ETABS, defining a steel India steel ASFE 250. Alright, having the moles of elasticity from the problem that is 2, so it's not 2 1, it's 2. Poison ratios is okay, and everything else is okay. 6 7 6 9 2 3 7 6 9 2 3, everything else is okay. Getting the modified design data, we have FE250 here, so the minimum strength is not required in this problem as we are providing a sort of axial compression or flexural compression, you can say. So effective yield stress that shall be, it can be like 250. Alright, that's enough, so you know, that's enough for now. Hit OK. Now getting into section properties, frame section, let's import an ISMB 350 right away from here. So ISMB 350, okay. Let's try to modify the property. Let's see whether all the properties are okay. So every properties are okay unless I converted that into a steel member. FE250, that's enough for now. Okay, now let's draw the thing. So picking up column. I can have this could be like an ISMB 350 right here. One more thing that we would like to do here is giving an axial joint load force in the z direction as minus 1 kilonewton right in here. I don't want to consider in sort of self-weight, so I'll be using load patterns. I'll be turning off the self-weight factor and modifying that load. That's all about now getting to analyze, and I don't want to turn this analysis into a dynamic one, so run it now. Getting to design, we got steel frame. I don't want to do anything here. I can simply get the start design check. That's it for now. Let me just right click on the structure and I'll be getting into the detail part. Only one thing that I'll be checking is the axial force, which RPD is 734, so which could be 733.85, that is it. So let's compare one more thing. So we can have buckling classes A and B. For A, we got alpha is 0.21 and 0.34, which is correct, 0.21 and 0.34. Lambda is 0.236. Lambda is 0.236. Okay. And for the other thing, for the other axis, lambda is, I think it is, where is lambda? Is 1.18. 1.18, which is also correct. Phi is 0.532. Phi is, where is phi? Phi is 0.532. For the other axis, phi is 1.375. 1.375. Alright, force is 225 and 110, so there is a slight variation in that. Force is not, force is 255. I might think there's something wrong in the factor of safety, I don't know. Anyways, the final force is almost equal